In this video, we're going to be working out a super thorough projectile problem, talk about all the concepts, strategies, and how to do all the calculations to find things like time, delta x, delta y, and even an angle theta at the end. Now, after we finish these examples, you should be a master at solving some of these projectile problems. All right, so let's start with some basic concepts. So we know that when something rises and something falls, we have something that's in free fall motion, which means that it is only affected by the force of gravity. No air resistance, no other forces involved. That would be called free fall motion. Now, when it's under the influence of only gravity, we have an acceleration of negative 9.8 meters per second squared the entire time. Other things we know is we know that when something has a certain initial velocity, as it returns back to the ground, it has the same exact final velocity, but it's negative because it's directed downwards. That's only if it returns back to the same height. Now, if it hits the very, very peak of its flight, then it has an instantaneous velocity of 0 meters per second. And one other extra little tip is because it's rising up the same distance up and down with the same acceleration, the time up is going to be equivalent to the time going down, again, assuming that it's returning back to the same height. Now, when we use all these different ideas, these are going to be just to analyze the vertical motion of the projectile. The projectile you see on the screen obviously has some vertical and horizontal motion going on, so this is strictly talking about the vertical motion. Now, with that vertical motion, we can use three formulas. All right, those are our three accelerated motion formulas. So if we're solving for anything that is relating to the vertical component of our projectile, we are definitely going to use one of those three formulas. Now, when you add some sort of horizontal component to it, like this or like this, the horizontal component is actually going to act completely independent of the vertical component. So we know that if something is going to be dropping straight down, it's going to accelerate at negative 9.8, it's going to fall down, and we can use the three accelerated motion formulas. Now, in the case where it has this arcing motion over here, it just happens to be scooting over a little bit as it's falling down and accelerating at negative 9.8. Okay, that horizontal velocity is actually going to be constant because if it's in free fall motion, remember, it only has the force of gravity acting on it, which is pulling the object down towards the center of the Earth. Now, once something is released, it doesn't have any other horizontal forces acting on it. Therefore, if there's no forces in the horizontal direction, that velocity is going to remain constant, whatever that number may be. Okay, same exact thing with the full arcing motion. If it's moving over at 2 meters per second in the very beginning of its motion horizontally, then it's going to be moving 2 meters per second at every point of its path because it has no forces pulling it left or right to change that horizontal component of 2 meters per second. So with that being said, if we're solving for anything in the x direction, then we're going to just use this one constant velocity formula, delta x over t. All right, those are some very important concepts to know. If you're not aware of those concepts and why you use certain formulas, it's going to make everything sort of difficult to solve these problems. Okay, let's clear the screen and start with these calculations. All right, now we're ready to solve for this red question. We'll call this question number 1. And the first thing you definitely need to do with a full range projectile problem is take your 10 meters per second and break it up into its x and y components. The reason you do that is because, just like we mentioned just a moment ago, the vertical and horizontal motion are different types of motion. One is constant velocity and one is accelerated motion. So we want to get the components so that we could use those with the proper formulas. So we have an angle of 60 degrees for our triangle, and we have a hypotenuse. So if we want the Vy, we're going to use sine, because sine of 60 degrees is opposite over our hypotenuse. Our hypotenuse is 10. And we're going to multiply both sides by 10. So it's 10 times sine of 60 And then our Vy is going to come out to 8.66 meters per second. Okay, that's going to be a number that we're going to use for a bunch of the different problems. So I'm going to go ahead and squeeze that over here. And then we're going to go ahead and use the cosine of 60 degrees so we can get the adjacent side. So adjacent over the hypotenuse. Again, multiplying both sides by 10. And then our Vx is going to come out to 5 meters per second. All right, let's go ahead and place that number up here. All right, now that we got that step taken care of, we can really organize our values and go ahead and set up everything to solve for our time delta x and delta y for question number 1. The first step we're definitely going to do is we're going to set up an x and y column so that everything that's going in the horizontal direction we place in here, everything that's going in the vertical direction we place over here. So our vertical velocity is going to be, or horizontal, excuse me, is 5 meters per second. That doesn't need a subscript because it's a constant velocity. On the y direction, we said it's speeding up and slowing down because of gravity. So this one does need the subscript of vi, or you could use v naught too. So our initial vertical velocity is 8.66 meters per second. Now, for our red scenario, it's reaching its peak. So we know at the peak, the final velocity is 0 meters per second because at that instant, it's not rising anymore. It taps 0 for just a moment. And then we also have a free acceleration all the time. The acceleration due to gravity, negative 9.8 meters per second squared. All right, so let's go ahead and find our time first. If I take a look at my 3 acceleration formulas, 2 of them, the first and second one, have time in them. It looks like the first one is going to be the most useful to me. So I'm going to say negative 9.8 equals my VF minus my VI over T. And I'm basically just going to cross multiply these two. And then negative 8.66 divided by negative 9.8 is going to give me a time of 0.88 seconds. All right, so that answers our first question over here, our time. Now, time is going to be one of the most useful things because since time is not a vector, it could be placed into this column and it could be placed into this column. So you're going to find that most problems you're going to be solving for time. All right, now let's go ahead and solve for delta x. And because we're in our x column looking for delta x, we're going to use velocity equals delta x over t. The velocity on the x side is 5 meters per second. The delta x is our unknown, and our time is 0.88 seconds. So we're going to go ahead and multiply both sides by 0.88. And then we have our delta x. Our delta x is going to equal 4.4 meters. Now moving on to our delta y, we're going to go back to our y column again, and we have to use the second or third accelerated motion formula because both of those have delta y's in them. At this point, I actually have my VI, VF, A, and T, so it turns out you could use either one. I'm going to go with my second formula over here because it's already set up for a delta y. The other one, I'm going to have to do a little bit of algebra. Either way, you'll get the same answer. So we'll go ahead and use this one, delta y equals VI 8.66 times our t that we just solved for, 0.88, plus 1/2 negative 9.8 t squared. Okay, and then I'm basically going to find the product of these and then subtract the product of these because the negative 9.8 makes that second product negative, and my delta y comes out to 3.83 meters. Okay, it should naturally come out positive because my projectile has risen to the peak of its flight, so it's moving upwards in the positive direction. All right, so for our first one, we found our components, which you typically need to do. You set up your X and Y component, which is definitely a must to organize your values. And then for this one in particular, we grabbed this value because that is specific to the peak of its flight. And then we use the a equals negative 9.8. That one's not very unique. We're going to use that for every single problem. Then from there, depending on what you're solving for, you work in the X or Y column. If you're working in the X column, you're going to want to make sure you use this orange formula over here because it's a constant velocity formula, or you use one of your green accelerated motion formulas for the Y side. All right, let's move on and then solve for our purple problem, which is this one. We'll call this problem number 2. All right, for problem number 2, I still have my X and Y columns here, which I definitely want to keep. And again, I'm going to start this one fresh and then put my X velocity here and put the initial velocity that I got from my initial little triangle. And then I'm ready to start question number 2. This one we're looking for time in delta X. The delta Y is pretty easy because the delta I would be 0. Delta Y would be 0 because it's returning back to the same original height that it was fired at and returning back to the same level. So if you want to just find the total range, this is the type of problem we're solving for, if it's returning back to the same height that it started from. Now for this one, it goes all the way up at 8.66, and then when it returns back down to the ground, it'll have the same velocity but downwards, so negative 8.66 meters per second. We're no longer using that VF of 0. Also, we still have our acceleration of negative 9.8 meters per second squared. Okay, anytime we have 3 numbers in our Y column, we can basically solve for whatever we need to. Anytime we have 2 numbers in our left column, we can solve for whatever we need to as well. So in this case, if we're solving for time, again, it looks like we're using that first accelerated motion formula. So acceleration equals VF minus VI over t. Okay, again, if we multiply both sides by t and then divide both sides by negative 9.8, it's basically the same thing as cross multiplying these two. And then I get a total time of 1.77 seconds. Okay, now if you wanted to, you could have took our previous time and doubled it. Our previous time that we got for Formula 1 was 0.88, but because of some rounding and stuff like that, it's not exactly double, but in reality, it's exactly double. When you go from the time up to its peak and then the total time like all the way back down to the ground, you could have just take that time from number 1 and doubled it. All right, so anyways, I'm starting it fresh, and I'm using a new VF so that you know that you can use the negative version of your VI to find your total time in the air. Now from there, we have our time 1.77 here, and we have it over here because time's not a vector. We can go ahead and slide that into either column. Now that looks good for my X column because I know that velocity equals delta X over t, multiply both sides by 1.77, and I am done finding my delta X. My delta X equals 8.85 meters. All right, so that is just a typical full-range projectile problem, solving for the total hang time in the air and solving for the range, which is our delta X. All right, let's move on to our last one, which is definitely the most complex problem. Now for this problem, again, I'm starting it fresh. We have our velocity of 5 meters per second here. We have a VI of 8.66 meters per second. We have our free acceleration of negative 9.8 meters per second squared. Okay, now this one, what we'll call number 3, is definitely a tricky one mathematically and conceptually. It looks like it is shot off a 3-meter platform, okay, which means the projectile eventually, if it's hitting the ground, its delta y is going to be negative 3 meters because it's dropping down 3 meters from its original position. So that's going to be our key number there. Now if we want to solve for time, we can't use the first formula because it's VF minus VI over T. We don't have a VF. We're going to go ahead and use the second one. So it's delta Y equals VI T plus 1/2 negative 9.8 T squared. Okay, we end up with a quadratic there, and we can go ahead and shift some stuff around, and we have 3 plus 8.66 T plus 1/2 times negative 1/2 times negative 9.8 is negative 4.9. That's our coefficient in front of the T squared. So we can do a couple of different things. We could use the quadratic formula. We could graph it and see the two intersection points of where it crosses the x-axis. Okay, both of those ways we will only get one positive t value. The only positive t value we'll get is 2.06 seconds. And just as a reference point, my total hang time for question number 2 was 1.77 seconds, so 2.06 at least checks the box that it's going to be a little bit longer than my previous time, but it's already starting to like pick up speed, so the time is going to be that much greater. That seems to make sense. All right, from there we can go ahead and place our time over here, 2.06 seconds. And 2.06 seconds. All right, so we went ahead and found our time. Delta x is going to be fairly simple. We still have our one constant velocity formula on the other side. 5 meters per second equals delta x over t. Multiply both sides by 2.06, and then we are done. And our delta x comes out to, let's see, it's 10.3. All right, now for our final velocity and our theta. These two are tricky ones, so here's what we're going to do. Let's go ahead and find our VF on our y side. Okay, there really is no VF for the x side because the entire time it's 5 meters per second, so there's no VI or VF. All right, so let's go ahead and find the VF on our y side. If we want to do that, there's multiple ways we could do that because we have every single number we need. I'm just going to go ahead and use our first formula and say that acceleration equals VF minus VI over t. All right, so algebraically, what I'm going to do is multiply both sides by 2.06, and then we're going to add 8.66 to both sides after I do that, and then I get a final velocity of negative 11.53. Whoops, 53. Okay, now the tricky part is if you were asked for your VF, you might think that's your final answer, which is actually not. This is the part where you definitely have to really think it through, because you have a vertical velocity and a horizontal one. So if you take a look at what it looks like right over here, it's an angled vector. So your actual final velocity is an angled vector. It's not just a vertical negative 11.53. So what we're going to do is this. We are going to take that 11.53, and then we are going to add the other vector, which is the constant velocity of 5 meters per second. Whenever you add vectors, you connect the starting point of your first vector to the tip of your last one, and then that resultant or hypotenuse is going to be your actual final answer. All right, so we're going to take the square root of 11.53 squared plus 5 squared, and then that's going to give our VF, because if we do a squared plus b squared equals c squared, where our VF is like our c, then we're eventually going to take the square root of the square of both of our sides combined, and then that way we get our actual VF of 12.57 meters per second, our actual angled vector. Now, what we're going to do from there is if we want to find the angle, we can find the angle theta right over here. And what we're going to do is use the inverse of tangent for that one. So if I use the inverse of tangent, that's going to be my opposite over my adjacent. And that's going to give me 23.44 degrees. Okay, if you wanted the complement of that, then say for example you wanted this angle right here, because that's the angle below the horizontal, that would just be the complement of 23.44, which is just 90 minus 23.44. And then you would get 66.56 degrees. Okay, it just depends on which angle you want. Okay, either way, you're going to have to use some kind of inverse trig function. I chose to use inverse tangent because I already had my opposite and adjacent side already written in this triangle over here. All right, to sum things up, you definitely want to make sure you find your x and y components of your vector, kind of like what we did right over here and right over here. Set up your x and y columns so that everything is placed in the proper column so that you can use the appropriate formulas. We have this formula only working with our x column because it's moving at a constant velocity because there are no horizontal forces in our right column. We're going to make sure we use our first, second, and third acceleration formulas because on the right side we have the acceleration from gravity, which is negative 9.8 meters per second squared. From there you have to be careful plugging in numbers that are specific to what you're asked, and then plug them in, do a little bit of algebra, and then you have your solution. Hope that was helpful to you. Thank you for watching and listening.